Hello students, welcome again to the new segment. Remember in the last lecture we learned how we can actually transfer the data into the MATLAB environment using the read table function. And now in this lecture we are going a step ahead and we are going to apply our first machine learning algorithm, that is the nearest neighbor algorithm. So let's recall that how we actually read the table. So the first step was essentially is to read the data into the MATLAB environment. So now with the read table function we have read the data. If we want to have a look at some of the few instances of this data, right? So the first 5 rows corresponding to all columns, so it will display all the corresponding variable. So if you go to the documentation of this iris data set which we are using in our experimentation, you will note that the final variable in this case, which is var5, it represents the class labels, right? Iris, Setosa, and so on. Here in this data set we have 3 classes. So we need to use this variable as a class variable and these 4 variables as predictor variables, right? So in order to use and build a model using a KNN algorithm, the MATLAB provides you with a built-in function which is fitcKNN. And this function needs at least 2 arguments. The first argument is the table data structure which contains the whole data. And the second argument is the name of the variable which contains the class labels in this case. And remember, we need to enclose it in single quotes, and we need to mention exactly its name, right? Without the t variable. So normally we use this syntax t.var5 in order to access the variable 5. But here in this function we need just to enclose it in single quotes and mention its appropriate name. And then you need to return it to some variable which will contain different parameters of this model, right? So when you press enter, we have now the model M, which represents the KN nearest neighbor implementation algorithm, and it contains different parameters. So if we display M, we may have these different pieces of information, right? These different pieces of information include the predictor variable names, which the fitcKNN have used in order to build the model. The response variable name, which in this case is the class variable, which is var5. And then the class names, remember there were 3 classes, iris setosa and iris versicolor and iris virginica. And then the number of observations were 150, and by default the distance metric it used was Euclidean, and the number of numbers it used was, the number of nearest neighbors it used was 1. For those of you who are coming up with a computer science background, they may easily understand that M is a particular instance of this particular class, and there are different properties and methods associated with the model M or the instance of this class M. So for instance, if we look at some of the properties, so you may note that the number of neighbors, the distance parameter it includes, and so on. So if you can access these properties by M dot and then the property name. For example, if we look at the priors, so the prior probability represents the prior probability of the different classes, and all of these classes are returned in the order in which they appear here. So for instance, the first probability is the probability of the iris setosa class, and then the second probability, which is 0.33, it is the probability of the second class, which is iris versicolor, and so on. Similarly, you can access different properties such as the M dot predictor name, right? Sorry, we need to have exactly the same name that is appearing over here. So predictor names, right? So that represents the variable names which were used for making up the model. Similarly, you can have the class names, M dot class names, and this represents the name of the different classes that appeared over there, and so on. The other important aspect is the methods that you can carry out on this instance M of this class, and these are the cross-val, loss, predict, and so on. All of them will become relevant as we go on within this course when we try to actually evaluate the performance of this KNN classification and so on. So now let us look at some of the properties that we can change, the default properties. For instance, we want to change the default distance from Euclidean to Minkowski distance. So we can do that by using the dot notation with the model. So m dot, and we need to mention the distance, and now the new distance we want to have is Minkowski. So when we press enter, it is going to update the model with the Minkowski distance. And it can be seen within these properties of the M, that is the distance has now been updated from Euclidean to Minkowski. Similarly, if you want to update the number of neighbors, we want to update it from 1 to, let's say, 3, right? So the correct name is number of neighbors, so NUM. Remember, you need to include the exact name of that property. So now the number of neighbors have been changed from 1 to 3, right? So this way you can change the default properties of this model to some other properties. Now the next thing we want to mention is a particular method based on this model M, and that is the resubstitution loss. By resubstitution loss, we mean the training error. That is the error that this model will have based on the training data itself. So in order to use that, we need to use the function resubLoss and then pass to it this model M, which is based on 7 nearest neighbor and Minkowski distance. And we can assign it to some variable if we want to store. So when we press enter, we may note that it is 0.0267. If we update the number of neighbors for this model, and we update it to 5, and then we again run the same resubstitution loss, so then we may note that it has increased from 0.267 to 0.033. Again, if we update it to 3, we may note that it's going to further increase, right? So it means that with lower number of neighbors, we have more training errors, and when we increase the number of neighbors, the training error is going to decrease, right? However, we may not want in some cases to decrease it beyond a certain threshold. In that case, it will be a very overfitted model, and that is generally disliked in the machine learning community. In general, we want to have a model that is not overfitted onto the training data, but that's general in order to incorporate more instances in the future. Right? So that's how we can actually access some of its methods and some of its properties as well. So more of these methods we will cover in the next few lectures when we cover how to evaluate the performance of a particular KNN classifier. But for now, I will strongly recommend you to go through all the documentation of this function and try to have some examples and some practice using different data sets, and try to look at how the number of neighbors actually affects the performance of your classifier, and how different distance metrics can be used in order to build up the KNN classifier, the custom-made KNN classifier for your problem. Hope you're enjoying the course. See you in the next segment.